and welcome to this MOOC video for the Algebra 2 module at Ekli Mohamedou Haj University of Bouira. I am Dr. Boucha Lydia, and today we will study Chapter 2 on linear maps. In this short video, we will cover the definition of linear map, image and kernel of a linear map, rank of a linear map, operations on linear maps. At the end of this video, you will be able to identify if a map is linear or not using the definition, express the image and the kernel of a linear map, compute the rank of a linear map, analyze if a map is injective, surjective, and bijective. First, what is a linear map? A linear map is a function between two vector spaces that preserves addition and scalar multiplication. In simple terms, if we have a map T, then it is linear if for all vectors x and y and scalar alpha, we have the additivity property and homogeneity property. For example, the map in F1 and F2 are linear, and the map F3 is not linear because it does not preserve the origin. The map in F4 is not linear because it has multiplicative terms. Now, let's look at properties of linear mappings. Linear mappings always maps the zero vector in the domain to the zero vector in the codomain. It preserves scalar multiplication. Here, alpha in the definition is equal to -1. And it preserves vector addition. If vector x is written as a linear combination of vectors, then a linear map distributes over the linear combination of vectors, keeping the scalars outside. Now we present the image and the kernel of a linear map. The image of a linear map, also called the range, is the set of all vectors that you can get by applying the linear map to vectors in the domain. It shows us what outputs are possible under the map. Note that the image of F is a subspace of the codomain W. For example, if we consider the following mapping F, to determine the image of F, we set U is equal to x plus y and V equals to y plus 1. And for any pair U and V in R2, we can find a pair UV that verifies the image of the pair XY is equal to UV. And by choosing Y is equal to V minus 1 and x equal to u minus v plus 1, we obtain that the image of F is the entire R2. The kernel of a linear map is the set of all vectors that are sent to 0 by the map. It helps to identify which inputs collapse to 0 vector under the linear mapping. The kernel of a linear mapping is a subspace of the domain V. As example, if you consider the following mapping F, to determine the kernel of the mapping F, we need to solve the equation f of x equal to the 0 vector of the codomain. Here we obtain that the kernel of F is equal to the set that contains the pair 1 minus 1. These concepts of image and kernel of a linear map helps to determine whether the linear map is surjective, if the image covers the entire codomain, injective, if the kernel only contains the 0 vector. Now let us discuss the rank of a linear map. The rank is the dimension of the image of a linear map. The nullity is the dimension of the kernel of a linear map. The following theorem is an important theorem called rank theorem. It connects the dimension of the domain, the rank, and the dimension of the kernel. It also helps to determine whether a linear map is surjective, injective, or bijective. In fact, a linear map is called surjective if the rank of f is equal to the dimension of the codomain. It is injective if the rank of f is equal to the dimension of the domain. And it is bijective if the rank of f is equal to both the dimension of the. Now we present operations on linear mappings. Linear maps can be added, scalared by scalars, while preserving linearity. This allows us to combine linear mappings and construct new linear maps systematically, which is essential in studying systems of equations and matrix algebra. Also, the composition of two linear mappings is still a linear map, provided that this composition is well defined. Finally, linear maps have various applications in mathematics. For example, in linear algebra, they help study vectors and matrices and solve the systems of linear equations. In differential equations, they help solve homogeneous linear differential equations. In calculus, they assist in computing derivatives, integrals, and so forth. Thank you for following this video on linear algebra, and I look forward to seeing you in the next videos of Algebra 2. Happy learning!